Welcome to classes on organic chemistry. It is class number 17 and continuation of class number 16. And today's topic is haloalkanes and haloarenes. And today I have just chosen a reaction or reactivity of alkene, haloalkene or haloarenes. And it is so important class that if you have the knowledge on today's class, you can very easily solve each and every question, maybe your class exam or maybe any entrance exam. So minutely follow the class. The today I have skipped some of the small points on haloalkanes and haloarenes in my last class 16, and first of all I will complete this one. First one is extra on preparation. You had given a very few type of preparation in your text, and I have just given you. Today I am going to tell you something more, and which are very important, very often asked in entrance exams, also in conversion or your entrance exam. So number one, say CH3CH2OH, very well known reaction, and it is known to you all. Here HCl gas and ZnCl2 anhydride was used as a distinguishing test, and these reagents are called Lucas reagent, and the process of formation of alkyl halide from alcohol with HCl gas and aldehyde ZnCl2 is also called Group's process. In next chapter I will solve out all the solutions, and why zinc chloride anhydride is used I will explain. Today I will not explain. Number two, say a question very often asked in your exam. Question is of type this. You are asked to draw or name all the isomers of this. This is alkane, CnH2 plus 2, and which of this isomer will give you the single monohalogenation? So simple one is normal pentane, CH3 CH2 CH2 CH2. Number two is, I am just showing you 1 2 3 4 5. You place it like this, you will get C6H12, and another one will be this. Second and third one, which is this one. So let me explain some of the number of hydrogens. It is one type of hydrogen, and it is hydrogen carbon with CH3CH3, and it is also same type. 1 2 3 will give you same type of halogenation, substitution of halogen. One halogen will enter, either this. So we will give you only one product out of three. All the other product will be the same. So we need to know first number of type of hydrogen, that is 1 2 1 1 1, and this is so your answer here. If you want to halogenate it, if you replace hydrogen by chlorine, so you will get one answer, CH2Cl, 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 all the same, just in any place you give Cl. CH3, CH, CH3, CH2, CH2, Cl. 1, 1, 1. This will give you one product. Number 2, in place of that hydrogen you place Cl. It is second type of product. Next you place one Cl in place of one H. You will get third type of display substitution reaction of halogen. So out of this you will get three type of products. So also in N-pentane you will get a lot of monohalogenated product, but here you see all types of hydrogen are same. Am I right? Same type. So you replace one hydrogen CH2Cl, 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 CH2Cl. You need not to replace all. You replace only one, it will give the same result. So only one monohalogenated product is only be possible in case of this compound. So out of this we will write CH3, CH3, CH, CH3, chlorine. The answer will be CH3, CCH3, CH3, CH2, Cl. This is the answer. It is neopentane, neopentyl chloride. I am just telling the name. You can write neopentane, neopentyl chloride. So other isomers will not give only one product. They will give different type of product depending upon the different type of hydrogen present in the compound. But this all the hydrogen or carbon are of the same type. So we will just replace one chlorine, that is monohalogenated substituted product. Next one is sodium and ether. You are asked to write the product. So this will be very simple because it is Wood's reaction. So our answer will be CH3. I am writing adjusting in this way. I can write this in this way. Answer is very simple. You write the answer yourself. You join these two, CH3C CH3H, CH3C CH3H. You join these two. The answer is this: CH3C CH3 bond CCH3. This bond. The answer will be like this. Next one is HBr. You are asked to write the answer, or we need to find out reaction means alkyl halide. How we will get this one? Bond will be withdrawn, there will be minus, and this is plus, and this is minus. That plus will attach with this one, so we'll get CH3, CCH3, CH3 bond CH3. So that is withdrawn in this way. It is negative. Negative will get attached with the hydrogen positive H proton. That will give you this carbocation, and there will be shift of methyl before reacting of Br negative. Now Br negative will attach in this position. So these are the some of the simple things. With the help of this, we get alkyl halide of different type. So now I am coming to special two type of reaction of alkene with halide. Very simple reaction. CH3, CH double bond, CH2, chlorine. Very famous reaction. This is propene, and you are asked to do the reaction with chlorine at very high temperature. Whenever temperature is high of the order 773 Kelvin, you never do this mistake. You don't add chlorine here and here. Addition reaction is not possible. There will be substitution reaction, and that is allylic carbon. Allylic carbon. So the substitution will occur in allylic carbon. So you will write Cl CH2 CH double bond CH2. There, this double bond will remain intact when temperature is high. At very high temperature, allylic substitution occur despite addition reaction, in place of addition reaction. And one of the fact is that if you ask me, yeah, are not there any addition product? Yes, there will be addition product, but at the very high temperature, this addition product is reversible. Whatever you get, it will reverse back. So addition product is negligible. You will get the substitution product. This is called allylic substitution. It is temperature dependent, and please keep in your mind, very often asked in entrance exam. Another type of same allylic substitution occurs when you are given NBS, N-bromosuccinimide. What is N-bromosuccinimide? N-bromosuccinimide is, this is N-bromosuccinimide. This is free radical allylic substitution. Again, allylic substitution will occur here. From one hydrogen, one hydrogen will be replaced by one chlorine in place of this. So you will get CH2CO, CH2CO, and in place of bromine, that hydrogen from here will come here. It is succinimide, and in place of that hydrogen which has been replaced, one bromine will come. That will come here. Bromine, CH2, CH double bond, CH2. So there is fundamentally two types of reaction at very high temperature on N-bromosuccinimide. Very often NBS is given, you will not be given this one. Whenever it is given, you blindly substitute one hydrogen at allylic position and write BrCH2 CH double bond CH2. So these are the special type of reaction that to be bring in your notice, that while you get this type of reaction, you don't touch double bond, don't make any addition. Don't make any addition. You make substitution at allylic position, so you will get the correct answer. So this is all about the points which I missed out, or due to lack I didn't mention in the class number 16. Now I am coming to the main point: KCN aqueous versus AgCN alcoholic. Very famous reaction from your book, KCN alcohol aqueous or AgCN alcohol. What's happened when some reactions are made with alkyl halide is made to react with this? Answer: I am first showing you one important thing. KCl is ionic compound. When alcoholic or aqueous in position, so that KCl is broken into in this way. Am I right? And this part, this becomes so. You see, whenever you want to, this is nucleophile, this is nucleophile. When you want to make reaction with alkyl halide, you will get this is a nucleophile of ambident, that is in both the type, both through C and through N the reaction may be possible. So this is ambident nucleophile where the reaction through N and reaction nucleophile is attacked through N and through carbon is possible. Whenever you want to make reaction with say CH3, CH2, Cl, KCN aqueous, what's happened? You will get this nucleophile. So this has the possibility of attacking this substrate through C or through N. But here this attack CH3, CH2 through Cn. Ethyl nitrile, ethane nitrile, ethane nitrile. The reason is that when the attack is possible through C and through N, but here the attack is done through C because CC, that C and this C bond is more stable than C double bond N. C double bond Cn and CCl bond, so that CCN bond is more stable than C triple bond Cn bond. Hence, attack through C is seen. Attack through C occurs as CC bond is more stable than C triple bond C. So stabler bond is formed with CC bond. Am I right? But case is different. Very often this question is asked in your exam. But question appears when in place of KCN you are given AgCN. When AgCN is given, what's happened? AgCN is covalent compound. Due to this covalency, AgCN becomes in this way. So lone pair is here only. So only option left here is to attack through N, not through C. That's why here in this case your answer will be N, C. So first one is cyanonitrile, ethane nitrile, and that one is isocyanide. So this is the concept which is mentioned in your textbook and question very often asked KCN and AgCN, why there is difference in the product formation. Next point one is basic character versus nucleophilic character, that is basicity versus nucleophilicity. It is a very tough thing. It needs a huge discussion, but one simple trick I will show you. Basic or basicity or basic character, nucleophile, nucleophilicity, these are different things. Now base and nucleophiles all the same. A base may be nucleophile, nucleophile may be base. They have lone pair of electron, they have negative sign upon this. Both nucleophile and base are the same thing. So their character, if base is strong, it may be strong nucleophile. That is, their character may be parallel. If basicity is more, nucleophilicity is also more. If nucleophilicity is less, basicity is less. It is directly proportional. Sometimes you will find basicity and nucleophilicity is reverse. A weak nucleophile may be a weak base, may be a strong nucleophile, and vice versa. So it is a very tough thing. But simple thing I am showing you: CH3, O negative, OH negative. In the both the case O are same, they belong to same period, and having negative sign, so they are strong base, so also they are strong nucleophile. They are strong base, so also they are strong nucleophile. Another one, CH3O negative, CH3C double O negative, both are strong base and strong nucleophile, that is they are parallel. Strong base is strong nucleophile, am I right? But problem arises, say CH3 CH2 S and CH3 CH2O, these are negative ion. Here oxygen and sulfur are on the same group. So in terms of basicity, this is a strong base and this weak base, but this is strong nucleophile and it is weak nucleophile. Am I right? Another case, it is reverse. We have seen a weak nucleophile is a weak base is a strong nucleophile. CH3 CH2S negative is a weak base, but it is strong nucleophile. Another one, HF HCl here, mention the acidic character. This is acidic character, acidic order. Now what is order of basicity? Order of basicity is this. Now what is order of nucleophilicity? Order of nucleophilicity is nucleophilicity. So here you see basic character and nucleophilic character are reverse. So you please keep these things in your mind. Now if I want to correlate the relation of basicity and nucleophilicity, it needs a huge discussion. What is base? Base is the actually ability to abstract proton. This is base. And what is nucleophilicity? Basicity is the ability to abstract proton. What is nucleophilicity? Ability to release electron pair. These are two things. We know base is a nucleophile. Nucleophile is a base, but basicity is the ability to abstract proton. If a base is a strong one, then it can very easily abstract a hydrogen from the substrate. Then it acts as a base. And if this base is a strong nucleophile, then at this position it will attach. Now what does base did? Base did nothing. It attached with the proton. Say this is ammonia. We will get here reversible sign. That will be like this. Here it acts as a base. Now what does nucleophile did? Nucleophile very often they attach, a nucleophile attach with this. Maximum of you may not know the basic difference between basicity and nucleophilicity. The base is this always reversible. So it is thermodynamically controlled, and it is nucleophilicity is kinetically controlled. It refers to the speed or rate of the reaction is nucleophilicity, and it attaches to thermodynamically controlled equilibrium state is referred with this base. Anyway, I am not make the class lengthy. If I get the scope, I will tell a huge thing about nucleophilicity versus basicity. Now, the main part of this chapter reaction is on nucleophilic substitution unimolecular. Am I right? And this is in haloalkanes, and also haloarenes. And another is nucleophilic electrophilic substitution. Very often we will discuss here with arene compound. These are the very two things. And another place in your book, substitution versus elimination. Substitution versus elimination. This is the main fact discussed in your chapter. But please minutely, with patience, you please remain in the class from first to end, so that you can understand some new things in the class. If you are too much um, uh, based on the ready-made questions answer, you will not find the class comfortable. And if you want to boost your knowledge or concept in chemistry, you will find the class very interesting one. So minutely follow. So first one is nucleophilic. Nucleophilic substitution reaction. For aromatic compound, I am telling, give here chlorobenzene. And if I ask you whether nucleophilic substitution occurs in chlorobenzene or not, you very often will tell that under normal circumstances is it not possible. So nucleophilic substitution in chlorobenzene or haloalkane is not possible easily because of the fact that this pair of electron get introduced in the resonance process resonance, and due to this carbon and chlorine appears or gives double bond in nature, and carbon and C double bond nature, if it is double bond, so it is not easy to split this bond. So nucleophilic substitution under normal condition is not possible, though we'll explain some of the nucleophilic condition substitution in arene, we'll explain later on. And number two, here if substitution occurs in haloalkanes, haloarenes, that substitution may be SN1, SN2. I am telling the SN1 substitution would not be possible at all. Why? I will tell. Because simply, if you remove this chlorine, SN1 substitution means one will be substituted, bond will be broken, in place one nucleophile will enter. If you break this one, there will be plus. Am I right? So when there will be plus, the bond will be the structure will be very unstable, and due to this fact, nucleophilic substitution of SN1 type is not. This is a very long discussion. My main point is substitution if occurs, then how? So before substitution in arene, let me give you one example of substitution of haloalkane. So this is very simple type of substitution reaction, you very often know. Answer is this. So if you go to the mechanism you have got in first year, you will see there is first carbocation formation, bromine is removed, and second, in this carbocation is 3-degree carbocation, is more stable carbocation, the nucleophile OH attacks and we get this. So there is, these are nucleophilic substitution reaction. One is two-step reaction. It is, one is carbocation, other is attack of nucleophile, and it is first order reaction because the rate of the reaction depends only upon of the substrate, not upon this. So it is unimolecular substitution reaction of order 1. Number 2, this substitution sometimes gives rise to a racemization. Am I right? And the alkyl halide order of alkyl halide of this substitution reaction is 3-degree alkyl halide is more readily undergo SN1 than 2-degree than 1-degree. And here attacking reagent, that is nucleophile, may attack from back, may attack from front, but front side attack is preferable. So this is SN1 reaction mechanism. Now it is 3-degree alkyl halide. 3-degree alkyl halide. So now take the example of this is the answer is this. I am not showing you the stereochemistry, I am showing simple the answer, but answer is not so simple. Here there is no carbocation formation, there is intermediate formation, transition state, intermediate, there is a transition state. So it is first year, there it is in first year. I am not showing you the transition state. There is first transition state, and attack of the nucleophile occurs from back because it is negative and O is also negative. In front side there is very often repulsion, so back side attack appears, and a transition states in the in between the reactant and product occurs, and this transition state converts into the product. And since nucleophile attacks from the back side, the reverse umbrella shape, that is inversion, is seen in this type of reaction. Here inversion occurs. It is second order reaction because the reaction rate depends upon the concentration of substrate and concentration of the nucleophile, and here reversion or inversion occurs. Am I right? So this is simple about SN1 and SN2 of alkyl halide. So what is about substitution reaction in arene? Say number 1, first one is chlorobenzene, sodium hydroxide, 623 Kelvin, 300 atmosphere pressure. Answer is phenol. Actually Dawes process I have mentioned in our class. Say, see, under very drastic condition of about temperature and pressure, from this we get substitution product of sodium. From sodium hydroxide we get OH is replaced by this. So it is nucleophilic substitution reaction under drastic condition. Now if you want to make the reaction easier, then we will use a nitro group in para position or in ortho position. What's happened? These electron withdrawing group, this activates the ring, and the density of electron on carbon Cl is decreased. Thereby C-Cl bond becomes weak. So this facilitates the breaking of Cl bond at most is than earlier. So with minus I effect group, if it is attached in ortho and para position, temperature is less temperature of is not needed. I think it is 468 something. Will get this reaction, this product. So it is more reactive than this is more reactive than this due to the presence of this. Now if you use ortho and para position and make this till will again give you this, because more the minus I group, more is the deactivating and more is the CCl bond weaker, more is less is the density of electron on C of CCl bond, and at more is the CCl bond will break and reaction will be faster, substitution of OH will occur. Next and last reaction is substitution sometimes question comes, I will tell you. Here in this case, no temperature is given, you just warm it, you will get answer. Am I right? So what we infer from the reactions, that more is the number of electron withdrawing group in the benzene ring of haloarenes, more speedy is the reaction. Am I right? So but one thing we have seen, no group is attached with the meta position, because if electron withdrawing group is in meta position, the electron group in meta position does not have any effect on reactivity, and the reason is can be drawn with drawing the structure of aromatic canonical resonating structure. I can explain, but it will take time. I'm not confining my discussion on meta, but mind that meta has no effect. If meta position electron withdrawing group is there, it doesn't have any effect on the activity of haloarenes. So these are very simple reactions of substitution of haloarenes. Next reaction is electrophilic substitution. These things are very common, you have got in first year. I will do it very fast. You just follow me. One is chlorination. Plus so you know this is electron deficient. This is one chlorine will be withdrawn here, Cl will be plus, and since ortho and your Cl, that from Cl one Cl will be done in this way, will be given electrophile, and that electrophile will enter in ortho and para position, where one and next chapter, next structure one here, that is chlorination reaction. Number 2 is alkylation, and next one is anhydride. Again you are getting 2 here, this group will be, you will get CH3 plus, and this is electrophile, this electrophile enter will this position and this position, you will get 2 structure. Next one is nitration. Nitrating mixture is HNO3 concentrated plus H2SO4 concentrated. Nitrating mixture means NO2 plus, NO2 plus is electrophile, again CH3 is ortho and para directing group, one NO will be in ortho, another NO will be in para, one is here, another is here, you will get 2. Another is sulfonation, I am not showing. When sulfuric acid concentrated is added, SO3H will be entered in ortho and para position. These are all substitution reaction, electrophilic substitution reaction. These things are very simple and you need not to learn, because you have got these things in first year class. But in your chapter, one name reaction is given, which is Wurtz fitting reaction. Wurtz fitting reaction, in Wurtz reaction we have seen alkyl halide, you see Rx plus twice sodium Xr in dry ether. What's happened? These two combines. In first year you have got this, we got the answer like this. So in Wurtz reaction we have seen 2 alkyl halide groups of same type repeated, and in presence of sodium and dry ether it gives you alkane. But here Wurtz fitting, one is aryl other is alkyl. Say one is X and other is alkyl. Am I right? And dry ether is here. This is the answer. Woods fitting. Next reaction was fitting. In reaction, both are aryl. Am I right? In dry ether, diphenyl. These two things are extra. So we have done up to this much. Now, very important and tricky part of your reaction is stereochemical aspect. Stereochemical aspects of nucleophilic substitution reaction. This is very important. Many of you do not give much interest on this fact. Minutely follow. Before talking about stereochemical aspect, let me first define what is plane of polarization. Plane polarized light. Normal light or monochromatic light is consist of waves which vibrates on all planes. If this normal or monochromatic light are made to pass through nickel prism, then wave consists of in a single plane. These light where waves are in single plane perpendicular to the propagation of wave is called plane polarized light. Am I right? Normal light consists of waves vibrating in all planes perpendicular to the plane of propagation of wave. Am I right? If this light is made to pass through nickel prism, then the light waves moves in a single plane perpendicular to the propagation of light. That is called plane polarized light. Later we will understand why I have defined this. Plane polarized, very important concept, plane polarized light. Second point is optical activity. Optical activity. Substance or compound which is capable of rotating the path of plane polarized light either to right or to left is called activity. And phenomenon of rotating the path of plane polarized light either towards right or towards left, it's called optical activity. Once again I am repeating, the ability of a substance or a compound in solution to rotate the path or plane of plane polarized light towards right or towards left, is called activity, and the process or the characteristics by which it can rotate the plane polarized light towards right or towards left is called optical activity. At a bit later I will tell why I have used the term optical activity. Next one is chirality. Chirality or dissymmetry. From the term dissymmetry means the substance or object does not have any symmetry. What is plane of symmetry? Plane of symmetry is an imaginary line which divides the object or compound into exactly equal halves. It's called plane of symmetry. Am I right? So dissymmetry does not have any symmetric plane. Chirality. Chirality means hand. The word chiral, Latin word from it is for hand. Images. These things is connected with the two things. If the images of an object is superimposable, then this is called chiral. And if the object or compound does not have plane of symmetry, that is through which it can be divided into two equal parts, if this substance, object or compound does not have these things, is called dissymmetry. So dissymmetry and chirality are the same. It is an important concept for optical activity. So in other words, chirality also means compound of carbon where each hands have different groups or atom attached. Say it is C3H7, it is CH3, it is OH, it is H. It is, or say it is CH3, it is OH, it is H, it is COOH, lactic acid. Am I right? So here you see it is dissymmetric because in no way you can divide this molecule into two equal halves. Dissymmetric. And it is chiral because if you draw the image, mirror image, you draw the mirror image of these two, say this is mirror, you will get the answer like this. So this is object and this is image. Now if you want to place this upon this, you will see that cannot be superimposed. So these two, object and image, are non-superimposed. Am I right? Like this hand, this is hand. The mirror image of this hand is this. Now if I want to place those things, I will place in this way. So one thing is in this way, one other thing is in this way. So it is not superimposed, non-superimposable. So these two terms, these two objects and image are non-superimposable to each other. So the object or compound which are non-superimposable image with each other are called enantiomers. Enantiomers are the compounds which are non-superimposable with each other. And non-superimposable images are compounds having non-superimposable object image relations related are nothing but chiral compound, and that carbon is called chiral center, dissymmetric center, stereogenetic center, and that compound I have talked much is nothing but optically active. Now what is optically active? This compound in solution has the ability to rotate the plane polarized light if it is passed upon in this solution either towards right or towards left. So optically this compound is active. So chirality and dissymmetry and plane of symmetry are the minimum condition to define whether a substance is optically active or not. In exam, very often these questions are come. These questions are asked. So up to enantiomers. Now what are diastomers? Now I have drawn a structure. If the structure consists of two carbon, so one object and other. Now if the object atoms are replaced, changed, and then if I take another image, then that an image has a relation is called diastomers. So out of the relation of enantiomers, other relations of object and image by changing the side atoms and taking the images are called diastomers. Am I right? So now each and everything is concerned with SN1 reaction. That's why I am telling you minutely follow. Next one is your racemization. RACEMI, racemization. Mixing to enhance in equal amount gives inactive compounds. And the process, I am explaining this, two enantiomers, which are enantiomers means compound carbon having different type of uh, things attached in different four hands are called enantiomers. Sorry, are called dissymmetric or chiral carbon, and that carbon containing four different atomic groups attached to it is optically active. Now this optically active compound has enantiomers. If these two enantiomers are added up, mixed up in equal amount, then the final mixture is nothing but inactive. Final mixture is nothing but inactive. But say enantiomer A and B are two enantiomers. When gives you, if it is plus, if it is minus, you will get plus minus. So these two will give these two individually. This is optically active. Individually, this is optically active. However, whenever these two in equal amount are mixed to gives an inactive mixture. Inactive mixture. Now, then when enantiomers of the process in which enantiomers having plus and minus activity means rotating towards right, rotating towards left activity is made to convert into a solution of two compound. As a whole, this two compound solution is inactive, is called racemization. The compounds enantiomers which are optically active are converted into a mixture of compounds which are as a whole is inactive. This process is called racemization. When I will explain with example, you can understand. Say in previous type I have shown you this is chirogenetic center, stereogenetic center, chiral carbon, dissymmetric, it has enantiomers, so it is no doubt optically active because four hand has four different atoms or groups. This carbon is chiral center. So it is optically active. Means it has the ability to rotate the plane polarized light either towards right or towards left. Am I right? Then I want to make to means potassium hydroxide aqueous means nucleophile. So instantly we'll get the answer like this. Am I right? Very simple way we will tell this is SN1 mechanism. Am I right? But this is not simple. Answer is not correct. What happens here is when this reactant is made to react with the nucleophile, what's happened here is a carbocation is formed, and that carbocation P carbocation C has P orbital which is vacant C plus. So whenever there is vacancy in P orbital, so the possibility of nucleophile to attack the planar carbocation sp2 hybridized, no steric hindrance effect because it is plane. It is planar carbocation sp2 hybridized. The nucleophile may attack either from right or from left or from above or from below. This gives rise to different structure. This gives rise to different structure. One is say I am just assuming say if you assume this nucleophile attacks from right or left, if it attacks from right you are getting this, if this attack from left you are getting this, if it attacks from above OH will be above, if it attacks from below OH will be different. You may tell me that what is the difference, the product, the structure is the same. No, there is difference in optically active. This is maybe plus or minus. I have to draw RS notation. I am not showing it. This may be plus and minus. If it is say plus, it will move the plane polarized light towards right, and if it is minus, if it is plus, this will be minus. It will move in anti-clockwise direction to the same extent as the above compound has moved the polarized light towards right. If it moves the light at certain angle towards right, it will move the plane polarized light at same angle towards left. So this is optically active, this is optically active. The mixture, one is compensated by the other, is inactive. This is called racemization. Am I right? This is called racemization. So in SN1 mechanism, we very often get racemization provided if it is CH3HH or all are CH3 and Cl, then this is no longer optically active. It is no longer optically active because this carbon is not stereogenetic center, because it's CH3 you have got 3 equal groups attached to it. So our condition is that 4 groups or atom must be different. But if it's CH3 then you give only one product, your answer is correct. Before, if you add OH here, OH there, no matter, it does not have any optical activity. It can't rotate. If CH3 the product, either way you write, it will have no optical activity. That's why in case of CH3 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 Cl, we just write OH, one react product. We don't react one product OH here, otherwise where, because that carbon does not have any chiral center, so it has not the ability to rotate the plane polarized either towards right or towards left. So in the first case, if CH3 is 3, we write only one product, but if it is optically active, we will write two product, and this two product is optically inactive, though individually these two products one are optically active, but in mixture these are inactive. So this mixture is called racemization. Am I right? Very important concept. Very often you are confused with these things. Now, substitution versus elimination. Again, it is mentioned in your book. Substitution versus elimination. Before coming to elimination part, just elimination again, maximum of you don't know what is elimination. Simply you know one type of reaction, but you don't know. I am sure that maximum of you don't know what is elimination. So before coming to elimination, let me example substitution versus elimination. CH2 Br, say C6H5OH, and heat is given. Heat or boiling, you can write boiling, and you are asked to write the answer. First of all, what will you do here? Answer will be CH3, 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 plus. From this, you will get this carbocation. Am I right? This is the carbocation. But whenever you get this carbocation, before making attack of nucleophile, you see whether there is possibility of rearrangement, stability of carbocation. Yes, there is possibility. There is a shift of methyl group. Want to shift of methyl group. So you are getting CH3, C, CH3, C, CH3. Carbocation from 1 degree to 3 degrees due to rearrangement. So methyl shift you have seen. Now our next step is ethanol. Next step is ethanol. C2H5OH. It will act as a nucleophile. SN1, because here carbocation is formed, nucleophile will attack. So this is SN1. Always with SN1 we are substitution versus elimination. If substitution is SN1, elimination E1 will follow. E1 there is carbocation formation. There is two transition state. In E2 there is mononuclear reaction, molecular reaction. One transition state is there, no carbocation is there. But in E1 and SN1 there is carbocation. That's why SN1 competes with E1. Now, what is the reason of competition? I will tell a bit later. So first of all, what will happen? One hydrogen here. Am I right? This hydrogen will be deprotonated, and the bond will be inclined. You have got elimination product CH3, C, double bond CH, CH3. It is E1 reaction. From carbocation elimination is there, E1. So we are doing substitution, along with we are getting elimination. So maximum time with SN1 there is a competition of E1. I will explain later on what is E1, what is E2, what is beta substitution, what is alpha elimination. So it's beta elimination after I will explain. Now here what will happen? CH3, C, CH3, CH2, CH3, and here your nucleophile will be attached in this way, and this is plus, deprotonation occurs. Bond will be withdrawn in this way. So you will get C, C, CH3, CH2, CH3, or C2H5. It is ether. Am I right? It is ether, and that process is solvolysis. In your book it is given solvolysis. I am telling the solvent ethanol is used as a nucleophile. The reactions where solvent used as a nucleophile and gives the product is called solvolysis. Solvent is acting as a nucleophile, hence it is called solvolysis. So we started SN1 reaction, and in between of the reaction we have got an eliminated product, hence maximum time substitution S1 always accompanied with elimination reaction. Now let me clarify some of the product, some of the important thing which you very often do not know. What is elimination? I assure you that maximum of you do not know. I know many of the students, those who are following the class, and many of them do not know the details of elimination. Though details is not required, but very often in entrance exam these things are important because a lot of objective type of questions are being asked from this one. Now, a very short way I will try to explain elimination. Elimination reaction maximum if you don't know, I am telling it again and again. One alpha elimination or 1-1 elimination, and number 2 is beta elimination or 1-2 elimination, and beta elimination is termed as E1 further divided into E2 E1 CB. I am telling that elimination a bit earlier. I have this one is CHCl3, base is used, CCl2 dot dot. I am not writing all this. This dihalide carbene. So this is alpha elimination because from alpha carbon elimination is done. Am I right? That's why it is called alpha elimination. Now what is beta elimination? Very often you have got this one, beta elimination, CH3 CH2 CH Br. A base. Am I right? So one hydrogen here, and this is alpha. Hydrogen is lost, is removed. That's why CH3 CH double bond CH2 1 2 3. Am I right? So from beta one hydrogen is lost. It is called beta elimination. Beta elimination. Am I right? So simple alpha elimination. Very often you don't know what is alpha elimination. This is alpha elimination where carbene is produced from 1-1 position. Atoms have been removed. Am I right? Now we will be concerned with beta elimination because beta elimination has different type. One E1, other E2, other is E1 CB. I have already shown you that where there is possibility of 3D carbocation, though there is transition state, I have not shown you the mechanism of E1. There are transition state. After this you will get carbocation. Then again there is a transition state. After this you will get product. I am not showing you the mechanism, but till there is carbocation formation possibility is there. So when this one base, what's happen? This withdraws and this becomes carbocation, and this carbocation say this is carbocation that is deprotonated and bond is withdrawn in this way. So you get CH3 double bond CH2 CH3. Am I right? This is E1 type of reaction where carbocation is formed and it is rearranged after deprotonation of hydrogen. A double bonded compound is formed and that is called E1 type of elimination. It is two-step again reaction. E1. Now what is E2? E2 type of reaction. Earlier, the type of reaction is E2 because it was a single step reaction, CH3 CH2, CH2, Br. If there is a base, then this is alpha, this is beta. From beta carbon, one hydrogen is lost, and this is CH3, CH double bond CH2. One carbon here will be lost. One hydrogen here will be lost, and that occurs in a single step reaction. That's why it is E2 type of reaction, and it is E1 type of reaction, same as that of in some aspect SN1 carbocation, and after deprotonation gives you this. So one is E1, other is E2. Now one is, which one is U1Cb? 90% of you don't know what is U1Cb. Elimination, monomolecular, conjugate, base type. U1 is same monomolecular, C for conjugate, B for base type. So CF3 CCl2, if you use a base, I am telling you this is very uncommon, but I will explain a bit, only a bit. What's happened here? CF3 CCl2, carbanion is formed, and that carbanion is stabilized by electron withdrawing group. So one of the important condition of U1Cb reaction is that in the substrate there should be electron withdrawing group, like CO group, like F group, like phenyl group. There should be electron withdrawing group, because that electron withdrawing group will facilitate. When carbanion, there is excess of minus charge is there, so this will be electron withdrawing group, this will withdraw electron, thereby the carbanion will be stabilized. Am I right? The carbanion will be stabilized. Next step, what's happened? Next step, say you do one thing, F ClF2, this Cl2, this would don't here, this is removed. So you are getting CF2 double bond CCl2. So this is of U1Cb type of the reaction. So now my main intention is not to show you all these things, but a simple and thorough knowledge. I want to depart simple and thorough knowledge on U1 type of reaction, but the main thing is where from Sejaf and Hoffman reaction occurs. Now this Sejaf and Hoffman reaction occurs from beta elimination. Orientation in beta elimination. I am telling verbally, the more stable or more substituted product is dictated by two empirical rule. One is Sejaf, other is Hoffman elimination. So I am showing you the sequence where from these two things came. It is actually elimination, one type of elimination, alpha elimination, beta elimination, 1 2 elimination. Beta elimination is of U1 E2 U1Cb, U1 of the same type of reaction of SN1 type, E2 is the same SN2 type of the reaction where transition states occurs, and in one step reaction completed. And this is one U1 2 of conjugated base type of reactions when electron withdrawing group will be present in the substrate, so to stabilize the carbanion formed. Am I right? Now what is Sejaf and Hoffman? This is nothing but the orientation of beta elimination reaction dictated by empirical rule is Sejaf rule and Hoffman rule. What does Sejaf rule tell? Sejaf rule tell, everybody of you know, CH3, CH2, Br, CH3, say hydroxide. Am I right? What does the orientation? What does orientation? Orientation means to give the stable product. So this is alpha, this is beta, and this is beta. What does SIGF tells? SIGF tells in the both the beta, where is the less hydrogen is there, both the beta carbon, one has less number of hydrogen, this has less number of hydrogen. That hydrogen will be removed, lost out. CH3, CH double bond, CH, CH3 will be the stable. And if you remove one from here, where carbon has more number of hydrogen, it will also give one product, but this will be less stable. The more substituted, more stable, symmetric compound, it is more stable, because CH3 is a plus I group and there is double bond. Due to hyperconjugation, more the CH3 group, more is the stability. So more stable, and it is also symmetry. And other, if you draw here double bond CH2, it is unsymmetric. Symmetric one or substituted or more stable will be the maximum majority. This is given by SIGF. Now what about Hofmann? Very interesting. Hofmann, what about Hofmann? Say tert butoxide. Tert butoxide. Mind that it is a nucleophile, but this is a very branched compound and it is a very big, sterically hindered. So this one, as a nucleophile will not attack, it will be a strong base to extract one hydrogen. If the nucleophile is a strong and bigger one, sterically very big size, huge one, and the substrate is also a very complicated and branched, so it will at ease extract one beta hydrogen rather than attack as a nucleophile. So it is both nucleophile and base. Here it will act as a base because of steric hindrance if the nucleophile is big. So now the question, this is alpha, sorry, this is beta and this is also beta. In earlier SIGF case, both the beta the beta carbon which has less hydrogen, the hydrogen was released from that hydrogen. If you just recall, in SIGF rule, both the beta, the carbon which has less number of hydrogen, from here one hydrogen was removed. But here in this case it will be reverse. In the both the beta carbon, where the carbon has more number of hydrogen, one hydrogen will be extracted out by the base CH3, CH, CH3, CH3, CH2, CH double bond, CH2. Now hydrogen has been extracted from that beta carbon, and out of this to that beta carbon which has more number of hydrogen carbon is dictated by Hofmann rule as a stable one. Am I right? So this is all about the reaction of haloalkane and haloarenes. Hope you have understood the class or enjoyed the class with utmost interest. You please don't forget to subscribe the class, and in next class I will come with the exact solution of textual questions and a lot of solution from entrance exam.